Hello and welcome everyone, this is Benham, and in this video today I want to talk about covariance and correlation. You may already know these measures. They talk about the relationship between two variables, and when you compute using correlation you can get a value between -1 and +1. But when you compute using covariance you can get any value. So when we say any value, the number for covariance can range between -infinity and +infinity. And that's one of the reasons why people find it a bit difficult to digest, interpret the covariance value. And some of the weaknesses, limitations of these interpretation qualities are overcome by correlation. So let us see with the help of a numerical example. Here I've got Amazon and Apple stock price returns. So if you were to buy Amazon and Apple stocks, what will be your monthly return for 5 months for this period is what I have collected. So what I want to do, first thing first, I want to compute covariance here using the MS Excel given function, and then compute covariance again using MS Excel given function first. So I'm not going to touch the formula approach first, okay? So equal covariance dot as open bracket. I need to select the array which is giving me the return from my first stocks, and then from the second, which is Apple, close parenthesis, and I get this as my covariance. Now I do the same for correlation, but for correlation the Excel function is correl, and then again I highlight the same. Amazon stock returns, Apple stock returns, and I get this number here, which is 95.47%, not that far away from 100%. So what does that mean? That then basically means the degree of association between Amazon and Apple stock returns are very high, positive, as given by correlation. But what can we say about this number 0.24%? Again, as I said to you at the start, the covariance value are not that easy to in terms of interpretation. But of course, it is telling you that the covariance is positive at 0.24%. And when it is positive, it basically means when Amazon stock returns go up, Apple stock returns will also go up. When Amazon stock return will go down, Apple stock returns will also go down. So that's something understood using covariance, similar to correlation. So what does this mean? If you think in terms of the diagram, then when you have Amazon and Apple stock returns in your X and Y axes in the graph, then this should give you an upward sloping line, isn't it? So that's something you can see here that it would be the case. So XY scatter diagram is what I have done, and then let me just plot a trend line, and this is therefore an upward sloping. So that's something we understand from these values for covariance and correlation. Now let us compute this again, but for a different set of data. When I say different set of data, I will retain them as it is there. I'll just change the Apple. So let me change Apple into Tesla. So here I've got the Tesla return for these very months. So therefore, I am going to capture the data related to Tesla returns. So that's what I have done. I'm going to pull it down, and you will see covariance and correlation are changing now. Okay, so they've already changed. So now what has happened? Let's see what were these numbers before. Before 95.47 correlation. Now the correlation is, it has gone down 94. So it's small, but it has gone down. But what about covariance? Before 0.24, now 0.69. It has gone up. It is therefore telling you that a higher covariance value doesn't necessarily guarantee a stronger relationship. Okay? Because you saw here the correlation has in fact weakened. Okay? Covariance has gone up from 0.2% to 0.7%. So this is why we need to apply cautionary, we need to remain cautious when we make interpretation related to covariance value, because they don't define the magnitude of the relationship as well as that given by correlation, something to be remembered. But now the focus today is to talk about the covariance and correlation, and at the same time we also want to look into a number of other measures. Firstly, what I want to talk about is variance, and I want to compare it with covariance. So the formula for variance is here. So I'm going to copy it, paste it here. Let me make it a little bit small. And now I also have the formula for covariance somewhere here. Yep. I'm going to cut it and then paste it next to the variance formula. Make it a little bit smaller so that you can see. Now I want to talk about these two. Can you see anything similar? In fact, they are similar. Here variance is talking to you in terms of the dispersion of the data from the mean, but it is just related to one variable such as Amazon or just Apple. But covariance takes into consideration two random variables. Here in this case, Amazon stock return and Apple stock returns. But if you change the y, if you replace the y by x here on the numerator, you will see that they will become like this. That will become this one. So that's something I'm going to put here. So I'm going to replace y by x. This means I can overlap it. Now can you see this formula and this formula is exactly same. I can just delete it and put a square there, cannot I? So what does this mean? This basically means covariance of x with x, or here covariance of returns of Amazon with Amazon will be equal to variance of returns with Amazon. Okay, so you may have therefore made use of something like variance covariance matrix, and if you seek variance covariance matrix something like this, the diagonal is in fact the variance. Covariance of x and x is the variance of x. So diagonal here represents variances. Okay, that was just on the similarity, but we know very well that covariance is a measure that gives us the relationship if the two random variables, how do they move together. Okay, how do they covary? That's what covariance gives us. What I want to do next is compute. Okay, so let's now start doing some calculation. So let's first find out variance. So to find out variance, I need the mean, which is x bar and y bar. So that's easy to compute. I just need the total, and the total can be divided by the number of sample. So therefore that basically means to find out the x bar, I just need to add them together and then divide it by number, which is 5. Okay, I can copy it for Apple and I get these. So once I have the average, which is x bar and y bar, I can compute all of these columns very easily. And then I can also compute variance, and I can also calculate covariance, also correlation. So let's do that. So I'm not going to waste more time. I'm going to do this really quickly. X minus X bar, which is here. When I have it, I'm just going to lock it so that now I can copy it for apple. I can now square it as well. I can also copy it, so that is squared. Now the last thing is to multiply these two. So now I will be dragging it down so that I have this computer for all monthly returns. And from this point, because the formula says summation here, can you see this Greek sign? So I need to add them all together, and therefore I have these completed. So now I first want to compute variance, and the variance is here, which is equal to the total, which is this, divided by n minus 1, which is basically 5 minus 1, therefore 4. Okay, do the same for apple, and then I get this. Of course, if you wanted, you can also make use of the Excel function, which is var.s, to compute the variance for Amazon, and then you would get the same value, and you can do this the same thing for apple as well. Okay, so here I have applied MS Excel function. Here I have shown you the formula approach. Same answers. So we computed variance. Now remember, when we computed variance, what is the unit of measurement here? These are in percentage. Here is a square. So we obtain answer in percentage square. So let's say that they were like height of people, and the answer would be like 5 foot 9 inch square. It's nothing like a square. You want 5 foot 9 inch. Or you want, if you're talking something in centimeter, you want 20 centimeters. You don't want 20 centimeters square. Okay, so therefore it is important to bring the result into a standard unit, or in this case the original unit, which is just percentage, not percentage square. And if you want to do that, then what you need to do is just put a square root. So this then basically means what you want to achieve here is called basically a standard deviation, which is here. So can you compare the formulas for variance and standard deviation? Exactly same, everything except that there is a square root here. Okay, so in order to improve the measurement unit that we find in variance, we can make use of a standard deviation. So just do square root of variance and you get the standard deviation. Of course, if you wanted, you can also make MS Excel function, which is stdv.s, and then you can obtain the standard deviation, which is again the same. Okay, so now we've computed them. What we may as well like to compute is called mean absolute deviation, and that's something I've shown you here in the slide. So why not compute this as well? So mean absolute deviation is something easy to compute. Remember, however, when you compute mean absolute deviation, what you do is you add all values as if all the values are positive. Okay, there's no negative values. So in order to achieve that, what you need to do is equal sum, that's to add them all together, but add them assuming they are all positive, means they are all absolute. So these lines here are just telling you in absolute terms. So ABS is the function in Excel, and then take all the values, close parenthesis, and divide by number, which is 5, which is here, and you get this number here, that number there. That's mean absolute deviation. Now in terms of popularity, it is a standard deviation which is most widely used. Okay, so we just quickly looked upon 3 different measures of dispersion, and we are saying that standard deviation is more popular. If you ask me which is least popular, it would be mean absolute deviation. Not that there is anything wrong with it. It's just for various reasons, such as the measurement unit that standard deviation improves, and standard deviation is more widely used because when we make assumptions such as normality distribution, central limit theorem, and so on, the standard deviation you'll find everywhere. Next, what I want to talk about is our covariance. The covariance here we computed using MS Excel function, but how about computing it using the formula approach? So the formula approach to compute the covariance is here. So that's what I can make use of. So here I'm going to compute covariance, for which what I need in the numerator is the summation of these, which is already here, divide by n minus 1, which is 5 take away 1, which is 4. Now you may have a question that when we compute variance, we do n minus 1. When we compute a standard deviation, we do n minus 1. When you compute covariance, we do n minus 1. Why n minus 1? Why not simply n? The answer can be related to the degrees of freedom. Okay, so let me explain very quickly. Suppose you know that the sample mean from 3 different data sets is equal to 2. Okay, so that's something you know. Now this is 2, and then there are 3 n's, so 3 different set of data. So let's say the first set of data is 1, the second set of data is also 1. What is the third set of data? So that when you add them all together, you get, and find the average, which is divide this by 3, you get the same number as here, which is sample mean of 2. This now is not equal to 2. You need to make it equal to 2. How can you make it equal to 2? Only when this is equal to 4, isn't it? This means this number here has to be 4. It cannot be any other number. So what does that mean? That means the n's here can vary with this term n minus 1. That basically means these numbers can take any value. So this can be 2 and this can be 3. But then this number here must be 1. Okay, in order to get the same sample mean. Or you can say this can be 0, this can be 3, hence this number here cannot change. There is one number that cannot change, has to be 3 in order to give the mean of a 2. Okay, so therefore is the reason why when we compute the sample, because of this very reason, the sample can vary with this degree of freedom, which is n minus 1. And this is the reason why we make use of n minus 1 in the denominator. And this can also be understood if you think in terms of unbiased sample estimate that we need. So when we need unbiased sample estimate, we need to make use of n minus 1. So that was about the concept of degree of freedom, which requires us to make use of n minus 1 when we compute sample, covariance, sample, variance, sample, all those measures. Okay, so now very quickly on the correlation, because we computed covariance using formula approach, but we have not computed correlation using formula approach yet. So that's something we can do quickly because we already know the formula for correlation is here. So let's make use of that formula. So remember in the numerator again we've got this term divided by, in the denominator now, is square root of x minus x bar whole square summation times the summation of y minus y bar whole square. So you get the same number as this. Another I want to talk about explains the relationship of correlation with covariance. So this side here is correlation, the sigma 1, 2 is covariance, this is standard deviation, and this is standard deviation from the second asset. So if you make use of that formula, you will still obtain the same correlation. So for that, equal to covariance, which is this number, divided by the standard deviation, which is this number, times standard deviation, which is this number, and you get the same 95.472%. So you see there is a relationship between correlation and covariance. Now the last thing that I want to talk about is again related to the interpretation quality given by correlation. And this time I want you to refer to Markowitz given portfolio variance computation formula, something like this. So those of you who understand it, you would know that you can make use of covariance in the formula, or you can make use of the variance. Okay, those formulas you may have seen in the past, so I'm just making use of those formulas in order to compute the risk for the portfolio. When I say portfolio, I need more than one assets, and here I've got two assets, so therefore they are representing a portfolio of two assets. So I've computed the risk. When I computed the risk here, I'm making use of the correlation, which is here F9. So if you go and see here, yeah, that's the correlation that I'm taking, 95.47, that's in F9. Okay, but if you see the risk computed here, I'm making use of covariance, which is this 0.2%. But both ways, I'm just getting the same risk. That's fine. So I just want to make a XY scatter chart using this. So that's it here. I have it now. And what I want to do here is I want to add data, and this time I want to name it, let's say, covariance given. Okay, so the before one was correlation given, and which was in blue, and this is covariance given, and series X is this, and for series Y, which is return, it is this one. So now I have the diagram here. As you can note, the blue line is overlapped now by the orange line. Okay, so this is something we can see here. What I will do next, I'm going to take it up where I can also see correlation and covariance numbers. So these are here. I'm going to paste that diagram over here. We'll make it a little bit small so that you can see everything together. Okay, in the same screen. So that's what I've got. Now, what I will do, I am going to make use of the covariance number and correlation number. So let's say that I want to change the correlation so that the risk, which is in x-axis, can be reduced. You may know from the diversification theory that uncorrelated or less correlated series is better for risk minimization. So it is 95.47. It's too high. Let me bring it down to 60%. Let's see what happens. Oh, I can see the blue line now. This means the risk is being reduced. So how about I change it to 30%? The risk is further reduced because it is going towards northwest. So in a map-like thing, when it is going toward the northwest, those of you who have understood Harry Markowitz's portfolio theory, you understand that the risk is being reduced. And if they are negatively correlated, it's even better. So I can change it to minus 10%. So it's going further away towards the northwest. And when I'm changing them from the original, which was 95.47, I understand by how much, the degree or the magnitude of change that I'm imposing, I understand it. From 95.47%, if I change it to 10%, I understand by how much the magnitude of change that I've imposed here. But if I want to do the same with covariance, 0.2%, I cannot think easily by how much this covariance I need to change. So maybe I can change it to 0.15. Let's see what happens. Okay, it has gone a little bit on this side. But here it's so easy. I can say minus 80%. And it's something really towards zero in terms of risk. But here I cannot think that number easily. 0.009. You see, that is the problem with the covariance. But they both are very useful, hence the reason why we need to study them. But for this video, for your watching and for your time, thank you very much, and see you soon.